So, welcome, ladies and gentlemen, to our next semester of the Nečas Continuum Mechanics. And our first speaker is Malte from the Department of Mathematical Analysis here in Paris, and he is going to speak about self-contact for inertial problems in continuum mechanics.
Thank you, Martin, for the introduction, for the invitation. And yeah, I mean, most important thing is this, what I'm going to present to, I mean, first it's a bit of an older idea, and then the actual result is joint work with Antonin Češek, who's sitting over there, and Giovanni Gavina, who's in the US, but was here when we started this. So, okay, so let me start with my usual story. So, what's take your favorite elastic solid and then think about things you can do with it, and then see how far you can get. And so you can start bending it, you can start rotating it, you can squeeze it. I won't do it too much because this will get wet here probably. But the point is you cannot squeeze it into a point. It's the ones to prevent you from it. And so you also cannot like invert it into its mirror image. It's impossible. And so if you think about the state space of this whole thing, you end up in terms of like some deformation of a reference configuration, you end up with something that's completely non-convex, non-linear, non-anything. Like it has some linear tangent space in some sense, but that's the best you can get. And then this also reflects in the usual elastic energies you use for those large deformations. And you can always take these linearized models around a certain given deformation, but as soon as you get away from this, as soon as you bend this strongly, as soon as you turn it, that's gone, because you kind of need to penalize compression, but rotation should be completely free. Like if this has zero energy, this should also have zero energy, except for gravitation. And this non-convexity for me is a key thing to lots of continuum mechanics, at least for solids. And there's some fluids people sitting here who will tell me, no, fluid velocity is perfectly linear, but I would argue that the material derivative also gives you some problems there. But the point for solids is, if you want to use large deformations, then anything that's based on linearization or on fixed point methods can only ever work localized. Like, sure, you can linearize around a point, but around a certain deformation, but this will not tell you about a completely different deformation. And all those standard fixed point methods you think about, like, I mean, Banach fixed points need some contraction, which means, okay, probably means you're close to where you started, that you can get this contraction, or, well, Schauder relies on the convex set, so it's out. And so the question is kind of, okay, what methods are still left to get to solutions? And at least for me, the answer is variational. And so you take your favorite direct method, you take some minimalistic sequence, find some bounds. If there are no bounds, you create bounds by relaxing your problems a bit. It's easy to get into there, and then you find a subsequence and have to work a bit for lower semi-continuity, but either your function is lower semi-continuous, or you just replace it by a relaxed version, which is. And then you end up with a solution, which is, of course, a very complicated story made very short. And then maybe for the students here, if you think back to what you know about this variation, and you think back, okay, there was this convexity and lower semi-continuity issue, but this was always convexity in the highest order terms. And if you think back about what I initially said, that what you have is a tangent space of the deformation. Like You can change your deformation slightly in some directions. You just need to be a bit convex in that direction to have the lower semi-continuity. That's kind of the idea. And then there's also an extremely ugly auxiliary problem that your minimizer might not even satisfy any equation. So that's the first abstract consideration I want to get into your mind. Now the second one, what I would call the three regimes of continuum mechanics. So they're static. You just take your solid and you have some forces on it, you get it into a minimized configuration. That's the standard example of a minimization problem. It's extremely well studied. You have the clear formulation as a minimization problem. You usually get some equation. So by the way, since I'll be using this a bit, E for me will always be some purely potential energy. dE will be its Fréchet derivative. I'll be doing this rather abstractly. And eta is the deformation. Okay. What's the second regime? Well, it's the quasi-static. So you take this, you have some time evolution, but it's slowly. Like if you bend it, it wants to bend back, but it will not immediately snap. It's minimal state, but it kind of resists changes a bit. So what happens there? Well, you add the dissipation to the whole thing, which is going to be this R, which is a bit technical, or you can just think of any abstract gradient flow, because that's ultimately what's happening. You're trying to get an energy small, but you're penalizing movement by a bit. This is a gradient flow. And this still can be done variational, but the idea is you iterate now, you minimize stepwise. I'll mention the details later. So that's still fine. And this is also very well studied for lots of problems. But then there's the final regime, the dynamic. You take your solid and you start throwing it around. And suddenly there's inertia in the game. And there everything is different. Because there is this weird way where there is actually variational structure in the original sense. If you look to the works of Euler and Lagrange, then that's the original Euler-Lagrange equation. All the people who do physics still, for them, a Lagrangian is some space-time functional. The problem is, it turns out not work if there's dissipative quantity, and B, more importantly, I deliberately start with the direct method. So for a general solid, this will be no minimization problem. It's basically like the wave equation. The wave equation is a critical point of a functional of like time derivative squared minus spatial derivative squared, but it's not a minimizer because the function has no minimizer. And so when people have been studying dynamic problems, usually go back to the non-variational method. You do your Galerkin approximation. You maybe make your problem a bit more specific, a bit more rigid, that you can use some fixed point methods, and depending on the game. But I kind of want to look at the general solid without throwing it away. And there it gets really complicated. And so we came up, basically, Barbara Benešová, Sebastian Schwarzacher, and I, with a weird method to do variational things for inertia, which is kind of the first ingredient for what I show you today. And the question was kind of going back to, okay, the static problem is just minimization. The quasi-static problem is we do this time-stepping scheme, which is rather similar, so I can explain it in one slide. So for basically a given step size, a given in time, a given configuration. We find the next configuration by minimizing this function. So you minimize the energy plus some correctly scaled dissipation, and yeah, the forces we don't care about yet. And then you get a solution. The solution hopefully has an Euler-Lagrange equation. As I said, this can get difficult. And then you see, okay, the Euler-Lagrange equation is this, which is kind of the equation you already wanted to find. Like it's a discretized time derivative now and there, but otherwise it's not. It's fine. And so you could say, again, if I want to start this dichotomy between PDE and variational, seeing myself on the variational sides. If you want to take the PDE look, then you could say, okay, if this equation makes sense, this is the PDE, you just take the PDE and work with that. Why the minimization? Well, the trick in the minimization is you get an estimate for free. So comparing your deformation, like your minimizer, basically, your eta k plus 1 with eta k gives you this inequality. So, because if you're not moving, there's nothing to be dissipated, the second term vanishes, and you kind of get, okay, the previous energy is larger than the new energy plus some dissipation. This telescopes, again, ignoring the forces, they're not hard. And then you get some nice uniform estimates if you have some coercivity, both on the energy and thus on the space of your function as well, on the discretized time derivative. Yeah. And this works basically whenever. There is this famous book by Ambrosio, Gigli, and Savary about gradient flows in metric spaces. It's basically this method. Just do it. It works for quasi-static. And the problem is dynamics. Can we try the same for dynamics? Sure, we can try. Add another extra term. Try to do the estimate from before and fail miserably for the energy estimate. Because no matter how you do it, you get one extra term that doesn't sum up. Because if you compare with eta k, you're comparing running along with suddenly stopping. It's not a good competitor energetically. And there you fail. And then you say, okay, comparing with stopping is not good. I need to compare with uniformly running along. Maybe. Then you get something like this, which, if you know more about the energy functional, is already fine. But it's not quite something that telescopes. It's something where you have to say, okay, I somehow need to estimate this E again. Which, in general, if we want to look at a general situation, it's not possible. It's works perfectly, for example, if E is a convex energy, which is not. It's not. And you can reverse the argument, start with the equation, but there's actually precisely the same problem. You need to estimate then this term if you test the equation with the discrete time derivative. And this works for convex problems. This works for convex problems, but without convexity, this term doesn't help you that much. Like, again, take a very specific problem, you can do very specific estimates to make it work. But the only way to get a good estimate is kind of if you only test on the continuous level. But you cannot get to the continuous level here because you need an estimate to send time step to 0. And we thought long and hard about this until we kind of had this weird idea to do both. Like to have a time step and a continuous equation, which is this weird monstrosity, which looks like the problem the problem with inertia. But instead of the second time derivative for the deformation, we take the first time derivative and then a discretized derivative of it. And then the general plan is, again, weird, but it works. So you just look at this equation on a very short interval of length h, where h is sometimes 10. It's a continuous equation, you could do this, doesn't matter. But on this interval h, because there's this time delay with the minus h, this is just an added force, this term. And the other time derivative comes from potential. We're perfectly fine with this, no worries. And so this is a gradient flow with forces. Gradient flows with forces, this is quasi-static machine. This we can solve. And we get a solution. And now we have a continuous equation. The continuous equation we can test with the time derivative, ignoring some details about regularity here. And if you do this, we get this estimate, where I'm a bit cheating with notation, but the key aspect here is you get something that almost looks like the kinetic energy plus the potential energy plus some dissipation stuff that I won't go into detail here is less than what happened at the previous step. So this is good. This gives us, again, if there's some coercivity, gives us uniform estimates, which means we have a uniform estimate on the interval 0h. If we have a uniform estimate on the interval 0h, well, then on the interval h2h, our time derivative at time minus h is right-hand side data. It's given. So we iterate, and so on, and so on, and so on. And this estimate's telescope. It's uniform in h, more or less, if you ignore those weird average integrals. And you can do a lot of theory, and it's not that hard to show, okay, you can set the limit h to 0. So that's the general approach, which maybe possibly bored some people here because I presented it some time ago already. But we kind of need to set the stage for the rest. So basically, if we want to get to a dynamic problem and do it variationally, we need to go step by step. We need to understand the static problem and its minimizers. Then we can say, okay, we iterate now, like we do this time stepping thing. We can solve quasi-static problems by iterative minimization, which means we can solve these gradient flow types problems, which means with this weird trick, we can now solve problems with inertia. And now we get to the problem I actually want to talk about, the problem I put in the abstract. So I was talking in the beginning about the state space of some deformation. And I omitted some peculiarities of the problem. Like, okay, I cannot push it into a point, that's one thing. But you can also, I mean, you can bend it so that it touches itself, but you cannot bend it further. It's not allowed to self-intersect. Or you can have some fixed obstacle, and then you throw it against the obstacle. It should bounce back if it's elastic enough. We learned this in school. But then the thing which kind of sparked the initial discussion is you learn in school that it bounces back. Like the rubber ball bounces if you throw it against the wall. But if you think about the explanation for it's elastic and therefore bounces, it's kind of circular. And so what started this was kind of, okay, what if we go from the most minimal assumption? So minimal assumption is this thing I just showed you. I can bend it so that it touches, but I cannot bend it further that it self-intersects, or that it intersects with the obstacle. And it turns out that for a bulk solid, that's enough. You get bouncing from that, but to get bouncing from that, you first need to get existence of weak solutions. And in particular, existence of weak solutions, which always fulfill these conditions, that it cannot self-intersect. That's the hard thing. That's, again, if you think about all those methods like Galerkin and so on, doing it in such a way that you allow up to contact, but you don't allow anything past contact, is extremely hard in an approximation. But it turns out in minimization, it's not so hard. So since this is the Nečas seminar on continuum mechanics, I have to mention Nečas, but I would have mentioned it anyway, because that's the condition for non-self-intersection that we use, the so-called Nečas condition. I corrected the mistake when I presented it last time that Stefan complained about, but now he's not here, so didn't even need it. So what?
I am here, just online.
Sorry, didn't see you. But yeah, I put the non-constant in there just for you. Okay, so what's the idea? So the idea is basically a mapping theory argument. So you say you have the reference configuration, and you draw this picture anyway. Q, and you have the deformed configuration, and you can never draw this correctly. And it might be an ugly thing like this. And now you say, okay, we all learned, like in the first semesters, there's an easy way to calculate the volume of this thing by pulling it back to here and integrating over the determinant. But actually, if there's some overlap, if there's some self-intersection, then integrating over the determinant counts the self-intersection twice. So if you say this should be equal, then this thing is not allowed. So can have contact, but it cannot go further. And so this is the main admissibility condition I wanted to think about. I mean, there's some other stuff, like it should be a finite energy, which in particular will prevent us from having weird issues with the determinant later, and it should satisfy some boundary conditions if we want boundary conditions. I mean, the fun thing with solid mechanics for inertia is you can actually do it without boundary conditions at all. It's not like you need to fix it somewhere for things not to break. And then if you start thinking about the static situation first, it's basically obstacle problems. And I like to think about this very abstractly. So central questions are questions, okay, if I treat my set of admissible deformations as just some abstract manifold in some sense, then as long as I'm in the interior of this manifold, I'm fine. This means kind of I have no contact, I can deform a bit in every direction I want to. It's more or less the classic case. But then there's this boundary set where some directions exist where if I deform in that direction, I get some overlap. I violate the Nečas condition. And then abstractly, I can think, okay, this means there's some tangent space, like in the manifold with boundary. That's interesting. that I need to study, and those conditions always produce Lagrange multipliers, and the question is, how does this Lagrange multiplier look like? And then the idea is to go down this whole list from static to quasi-static to with inertia and see if anything breaks along the way. And then, since people tend to complain about this, I need to say beforehand, like I'm doing all this for second order materials. So the energy will not only depend on the gradient, it will depend on the second derivative as well. And there's good reasons to do this, because more or less otherwise everything breaks. That's the easy way to put it. So if you go back one slide, if you think about it, okay, this overlap is one way to violate the fairly Nečas condition. The other way is to violate it by having negative determinants somewhere. And if you're in the reasonable Sobolev space W1P for some P high enough, then still you can produce negative determinant on a very tiny set arbitrarily fast. Which is a problem. It's probably a problem we can live with some work, but we may not want to live with that yet. And then, much more importantly, okay, you want an energy which penalizes the determinant going to zero. Like compressing a solid to a point, it's not only impossible, it should be expensive. But then it turns out whenever you actually, you can still have finite energy with a deformation that has just at one point determinant equal to zero. Which leads to this weird situation that this could be your minimizer, but you don't have no Lagrange equation. Because, I mean, if you do the calculation, if your energy is something plus the Jacobian determinant to some A, then your Euler-Lagrange equation will involve testing some test function against all the other stuff, and then it's going to be the cofactor matrix times the test function, and it's just chain rule. That's going to be A plus 1. And that's a problem because you only have the integrability you gain from your finite energy. Then there's some factor in there, but ignore that. Okay. And then this alone is a reason to take higher order materials. But then the more important reason is that if you think about contact, and physically you get a contact force, and if you ignore friction, then this contact force should act perfectly in normal direction, which is reasonable. The problem is if you just have some first order thing, then the normal direction is of the deformed configuration is not a very well defined object. Because you would like to say, okay, it's the cofactor matrix times the original normal, but that might not be properly defined. It's definitely living on the level of the first derivative. So it can have jumps, it can change direction arbitrarily under the conversions we have. And so we're not going there, we're taking second order materials and saying, okay, this gives us a nice definition of the normal. The normal is uniformly convergent if we have some sequence of configurations. And personally, I claim this is still state of the art in those problems, and so we're fine. And then there's another downside, like to make this work properly, you would also have some Q growth no, should be P growth, I think, but anyway. Just messed up the letter, which is non-quadratic. Have nice coercivity, which means later on your differential operator is a nonlinear operator at highest order, which can introduce some other difficulties. Okay. That being said, let's get back to the context. So I talked about kind of quantifying, classifying these test functions. What is the abstract tangent space in my space of configurations at the point of contact? And so just looking at self-contact, what we kind of get is that you need to look at the normals and this point and say, so first of all, these 2 points here translate to some points in the reference configuration that are quite far apart. But essentially, you're allowed to move in any direction that separates them, that moves them along uniformly, but you're not allowed to move in a direction that pushes them further, which is this simple condition. And this condition already turns out trickier than one might think that it is. So, for example, you would think, okay, some abstract convertible direction, some good test function means I can go a little bit in that direction and still be fine. But it turns out here it's not the case. Which this example is for. So if this is the one half of the solid, and the other one looks like this. They're touched here somewhere, and it's over there. Then, in terms of this condition, it's perfectly fine to keep, say, the right hand side stationary and move the left hand side down. And with this kind of concave picture, no matter how little you move down, we have overlap. But again, if you use abstract differential geometry, which has been extremely helpful as a tool here, you think about, okay, the definition of a tangent vector is not going in that direction is allowed, it's just there is an allowed curve, the curve of possible deformations that goes in the same direction. And that's perfectly fine. I mean, I can go down here, but go backwards here with some squares of the velocity algorithm, then it's fine. I mean, I'm mostly trying to point out that this problem is rather tricky. But you can do this. You can take this characterization, and then you say, okay, if I minimize the problem, I don't get an Euler-Lagrange equation anymore. I get a variation of inequality. Because basically, I'm allowed to test into the good directions in this cone. And I'm not allowed to test into the directions that get overlap. So instead of the derivative being 0, I get the derivative being larger or equal than 0. And of course, if phi is admissible and minus phi is admissible, I get equality here. That's the standard trick. Okay. And then you think about how to relate this back to physics. So I've been talking about this contact force already. The idea is kind of if you have contacts, physically what's keeping you from pushing further into overlap is some contact force. So it's a weird force because it's a force that for us lives in the reference configuration. which means it lives here and here, but it's basically the same picture. But somehow this part cancels this part because you need to have conservation of momentum and everything. And it can only live on this part that's actually in contact. And since it can only live on this part and has to produce something, the best we can expect it to be is some measure. It cannot be something nice. It will be concentrated because that's actually what turns out to produce the bouncing. It actually only lives on a set of lower dimension. Okay, then here's a nice tool we had in the constructions and the proofs, which I'm actually not using now, but I wanted to mention because it's quite useful. Because if you want to estimate this contact force, like you would say, okay, it's a force, it acts in normal direction. So to find its norm, I multiply it with the normal vector. Would be the right thing to do. The problem is that initially you don't know it's a measure. It's just some distribution, which if the deformation is on the order 2, like as two derivatives, it will be the dual because it kind of comes from there. And so it's a distribution of order -2. But the normal is on the order of the first derivative. So it lost an order. So you cannot test with the normal. But it turns out to do this estimate, you only need what we like to call an almost normal. I don't know if it's already been used somewhere else, but turns out you can always find a smooth function easily that just points roughly in the direction of the normal. And for all estimates on this contact force, this is enough. Okay. So I mentioned going from the static case to the dynamic case. So let's start with the static case. This was shown by Palmer and Healy, I believe, that in the static case, your contact force is actually a measure. And I really like this proof because it feels like some argument I may have seen in some optimization class way back as a student, but linear optimization. It just works out. Okay, what's the idea? So in this whole graph, you should think of W as the distance between contact. So if you go further to the right, this means, okay, we managed to get some distance at certain points. That's why W is a continuous function. Away from the contact. And basically this M plus here corresponds to the reachable set. So it means, okay, there is some direction to go in, to test in, where we may spend some energy L, or possibly less, and create some distance W. And this lives more or less in this quadrant because, I mean, it's always definitely possible, you should point to it, it's always possible to waste energy and gain negative distance. That's the worst case, that always works. It might be possible a bit to lose energy and produce overlap. Sounds reasonable, that's what the contact force is preventing us from. And it could be possible to spend a bit of energy and actually get some further distance away. And to this point, in contrast to the set, you have this forbidden set. Like, this is the set where you gain distance and you gain energy. And since we started with a minimizer, it's impossible to get into that set. Like, that would contradict having a minimizer. Which is also where this almost normal function comes into play to prove this. And you look at those two sets, And with a bit of work, you can show, or Malte could show that in general, those are convex sets or convex cones, which basically only intersect at a 0. And otherwise, there's no real overlap. And so this means there's a separating hyperplane between those sets. And since the space this is in is the continuous functions times R, this means the hyperplane is in the dual, or given by something from the dual. So it's the hyperplane is the kernel of some measure times the vector times R. And the last step is you find a point that's here. You explicitly construct this for your situation, which tells you, okay, this hyperplane cannot be vertical. That's the enemy. Because if it's not vertical, then we can, should be lambda here, not L, but you can divide by lambda and construct this as your actual contact force. So that's the Palmer-Healy argument. And we have some slight improvements, and that we actually quantify where this point is. This turns out to be crucial in terms of the energy of our configuration and so on. And this gives us an estimate on the contact force. Okay, they get to this static result, where they basically say, okay, this nice enough energy, whatever it precisely is, I don't care right now, some second order thing, has a minimizer which solves this equation with the contact force. And they're very happy about it. And then I need to be really careful to say nothing wrong now that both people involved are in the audience. Stefan Krömer and Tomasz Rubicek extended this to quasi-static, where they say, okay, the quasi-static also works. But in their paper, what's left over is not a measure, but just a distribution. And I mean, the first thing we were able to do was to slightly improve this, which actually turns out not to be hard. So what's the difficulty? What's the problem that occurs? You have this nonlinear operator, if I is smaller than E. You want to have some monotonicity, you want to do your Minty business there, but that needs the equation. And constructing a contact force in the easiest way also needs the equation. And you cannot use the equation twice completely for both. But the trick is, if you look carefully, then you can kind of do this monotonicity with only what happens in the interior of the solid. Like it's enough to be able to test with something that's supported in the reference configuration. But in the reference configuration, all test functions are fine. And so you get convergence of your DE from your approximation. And then even further, you don't need to construct your contact measure from that, which would get you into all that work with Palmer-Healy again. But you can also say, if you do what we did, get an explicit estimate on the contact force as a measure. It's actually L2 in time and measure in space, and find some compactness closure argument for contact forces. Then you know, okay, all three terms converge in this equation, and so the limit is also nice. And how am I doing with time? So some time, I guess. Yeah, let me talk a tiny bit about this compactness closure result. So assume you have some nice contact forces, basically says, okay, if my deformation converges at least at level C1, which is again where the second order material comes in, because having some coercivity in the second derivative allows us to say that the first derivative converges nicely. then the limit thing will be again a contact force, and it will be a measure and everything that's bound before that. And the proof is rather simple, because you can always use the compactness theorem for measures to get something for the limit if you have those uniform bounds you need to work for. Then you can show that if you have a sequence of deformations, then the only way, there are two ways to have non-injectivity in the limit. One is you're coming from somewhere where there's already some contacts, in which case you kind of get a limit contact measure from there, or the other is you just touch in the limit, in which case there's actually no contact measure. So that's fine. That direction works out. Yeah, then we use that the normal converges uniformly. We can identify this measure with the right limits, and this action-reaction principle that the forces cancel actually follows from continuity. And then finally, let me get back to the inertial problem. So it's basically what I like about this trick, about this method, it's no work at all. Like, we understand the quasi-static situation, and it turns out if you understand the quasi-static situation, it's like your free boring estimates and a bit of work, depending on your problem, away from understanding the inertial situation. So basically, we use this quasi-static result to construct solutions to this time-delayed equation that I wrote down. And then it's a bit weird. Okay, you don't get an equation. It's technically not a time-delayed equation, because we do it at the level of relational inequalities. You get a time-delayed inequality with the cone of test functions. But then if you think about, I should have changed that slide, but I didn't. If you think about, okay, if I have contact, what are some specific directions I actually have available? I mean, I want to test with the time derivative. The time derivative means I'm coming from somewhere. But that somewhere I was coming from is an admissible deformation, per definition. And so I can use this to test with the time derivative. And actually, it turns out you don't need this precisely in this form, but it's good enough. So you do the trick from before, you get the same uniform estimates. You take those estimates, you go to the limit. And there you're at. There is a weak solution to the problem with inertia, with a contact force that's a proper measure that satisfies this action-reaction principle and everything. And then you can take this and do some simple arguments why your rubber ball has to bounce. Because as I mentioned before, the basic idea is you have this weird phenomenon where at the contact, there is an infinite change in velocity. But the contact is a very small set. It's particularly a set of low dimension, which means there is no momentum on it itself. Like the momentum is spread out, and so there's no weird change in momentum. But yeah, let me not go into that too much. Yeah, here's some other results with similar techniques, which just should tell you that this technique is powerful. I don't know. It works. I'm still finding good problems to use with it faster than I can write them down. And with this, it was too fast actually. I can get to some closing remarks. So what's the lesson? Like the idea is to closely look at the abstract argument without doing the abstract argument formally, as usual. Because you can kind of spend a lot of work doing the precise calculations for some precise energy and everything. but it turns out you actually don't need them. You just need to look at the general picture, find the right definitions, which took us longer than anticipated. And then you can construct problems like this one. For self-context, you can construct solutions rather easily. And the principle holds everywhere. You can think of completely different problems that have a similar structure where you can go in one direction until you suddenly can't anymore. This all should apply. There's, of course, a list of open problems, works in progress. So we just started more or less to work on less smooth boundaries. Like all the stuff on the paper is for a boundary where there's actually a normal in every point and stuff like this. But you could think of, okay, what happens with corners? Then suddenly also more than two parts of the solid can touch at the same time. Stuff like this happens. Yeah, I mean, since I'm still on Sebastian's grant partially, I always have to do fluid structure interaction. So we're actually planning to do this soon, to do some fluid structure interaction with contact, which also is a long, interesting problem. I've always been thinking about it. It's actually not that hard, I believe, to put friction in there. In fact, if you take less regularity, you could maybe even prove that friction occurs just out of the contact. I mean, if you think about it, friction often is just some kind of surface roughness that's scratching against each other. And all the way back in my mind, there are some applications of some of those ideas to the Jacobian determinant equals 0 at some point problem, but that's probably too hard. I don't know. There's been a bunch of people trying it for a long time, so I'm not claiming anything. Yeah, and then one last aspect I like to mention is that this whole method also kind of works as a general energetical modeling procedure. Because the only thing we put into the problem was an energy, a dissipation, and some kinematics in the sense of which directions are allowed and which aren't. And the dynamic equations just fell out from this and the method. And that's it. Thank you.